What we're going to look at now are some other examples of position tolerance zones and also how to locate a feature when we're trying to determine whether or not it's within position tolerance. So last time we looked a little bit at determining the location. We'll look at some more examples now, and then the effects of that position tolerance on the surface and how it's located. And finally, what happens when we add material condition. So in this example, we have a position tolerance zone, and we're trying to constrain the location of the feature, which in this case is a cylindrical feature. If I look at the specification here, I note that we're dealing with an axis, and therefore we have a cylindrical tolerance zone as indicated by the red shaded region. It has a static width of 0.01, and we have a datum reference frame, first A, then B. So we establish datum A, which would be the bottom surface. Then we establish datum B, which of course would be the mating envelope, the smallest cylinder that fits around B. And then we have to find the tolerance zone. In terms of where it should be located, it's going to be centered on the axis of B and of course oriented perpendicular to A. Well, what's happening with the surface as we see variation in the axis over here? The axis varies due to our individual processes that are being used to produce that feature. And now within this red zone, or cylinder, we allow that axis to vary both in orientation, shape, as well as position. The result is seen in terms of the virtual condition and the resultant condition. We have this 2D annulus looking down from the top here. As long as the surface of that feature is within that 2D annulus, we're going to say it is within position. And so the surface is varying as the axis is varying. In terms of finding the feature location, again, you should understand the notion of the mating envelope and also whether or not we have to orient the mating envelope under what conditions. On the left, we have a datum feature that we're trying to determine its location. For instance, if this was datum B in the previous example, and if it has to be oriented with respect to another datum, such in this case perpendicular, then we're going to find the smallest cylinder that fits with the constraint that it be perpendicular to A. If it is independent of datums, for instance the feature itself or the primary datum, then we won't orient the axis, as you can see here, the same part, but we'll find the smallest cylinder that fits around that part. Clearly the diameter here and the diameter here are quite different for the mating envelopes, as well as the orientation and location of the axis. Here we have an example of a slot feature looking from the side, and as we know, if we're trying to control the location of a slot feature, what we're really talking about is the midplane. So we're looking down the length of the slot and we're trying to control its location by controlling the midplane. So as the midplane moves left to right, the location of the slot changes. But really the slot is defined in terms of the sides. In order to determine where that midplane is, we're going to use a mating envelope, which is the largest distance between parallel planes that fit within that slot. The same is true if it's a solid feature, such as a protrusion in this figure. The distance, however, will be the minimum distance that we can enclose that surface because it is solid. So we'll enclose a box around our protrusion, and from that also find the midplane as in the previous example. So here's a slot specification where we're looking at the position of that slot. And the reason that we know we're dealing with a slot is we have a feature control frame attached to the dimension. And we can see it is a feature of size. We do have our datum references A and B. A, of course, being the bottom surface, which we would establish with the surface plate. B, we're going to enclose these two surfaces in a box. So we have two parallel planes. The smallest distance between those establishes a midplane going down the length of our part here. And now for our tolerance zone, we're going to create two parallel planes, which is represented here. So you can think of that as kind of a box over the length of the feature. And we center that on B. So these two planes describing the tolerance zone are centered, in other words, equidistant from B, datum B being a plane. The width of the tolerance zone, of course, is 0.1. If we look at the surface location, as the midplane varies within that red box, we can see the virtual condition and the resultant condition. Of course, because it is a slot feature, the virtual condition is the smallest slot. The max resultant condition is the largest in terms of surfaces. And the surfaces of the slot will vary inside these regions. So that's what we can expect in terms of individual parts coming out of our system. Feature location for a slot that's based on a mating envelope, as we saw in the previous example. Again, we can have two possibilities here. The one on the left, if the feature is being used in a datum reference frame, for instance, we have a primary datum, this bottom surface. Now, if we want to use this feature in our datum reference frame, we will have to orient this mating envelope with respect to this datum, and then find the largest box that fits inside of that feature. If, however, this feature is independent of datums, such as the feature we're trying to control, or it's a primary datum, then we just find the largest box that fits inside there, and as you can see, the midplane is very different than this one. So the location and orientation of that feature is changing depending upon its relationship with other features. Now, if we have MMC conditions, as we've seen before, what we're going to do is add in the additional tolerance that we would have due to the feature deviating from its maximum mature condition, or one or more datums that may be in the feature control frame that are also features of size. And we can represent that as a sum where we have the static portion here. This is the dynamic portion, where of course A sub I would be an actual dimension for a feature of size. M sub I would be the maximum mature condition for that same feature. Take the absolute value and then add them up. That would give us the width or size of our tolerance zone. So here in that shaft example from before, now we see that we have maximum mature condition both on the feature itself and on the datum. Therefore, we have to look at the spec and see, okay, what is the maximum mature condition for the feature, which would be 3.6, maximum mature condition for datum B, which would be 8.1, and then we measure using the mating envelope D and B. Of course, B, that mating envelope has to be oriented perpendicular to A, as we see, because A is primary. And then we find the mating envelope for the feature itself, and then the diameter of that mating envelope would correspond to D. Now we have the size of our tolerance zone, which we won't know until we actually make this part. In the slot example, we can add a mature condition to datum B because it's a feature of size, and of course the slot itself. So we see that here. Now we know that we have a dynamic tolerance. Here's the static part that we had from before. And now we find the mating envelope for the slot, determine its width, D. That's the actual. And then subtract out the maximum material condition, which of course would be the smallest dimension for this slot. For B, we're going to take, again, the mating envelope, two parallel planes, enclose those two sides of the part. Its maximum material condition would be the largest distance, which would be 80.2. And now we have our dynamic tolerance size. Again, we don't know the actual number until we make this part and then measure those features. So at this stage, you should know how to locate a feature based on a locating geometry. So we saw the use of a mating envelope to determine where that feature is. We also understand the notion of surface varying between the virtual condition and resultant condition, and the effect of material condition. Mating envelope is used to find the location of a feature of size, and we've seen that in a number of examples. The virtual condition will be a bounding envelope, and the resultant condition will be a bounding envelope for the surface. So we know the surface is going to lie somewhere in that region, and when we're thinking ahead in terms of our tooling and inspection, we're going to have to accommodate that type of variation. Material condition can be used when we have features of size, either the feature itself or datum features.